Okay, great.
Okay, recording's on.
Thank you, Arthur. Yeah, so we are continuing with our previous discussion on the many electron system, right? So I hope some concepts have already, been grounded and have already, have roots in our minds that, why we care about the many electron systems. So in essence, when we talk about electronic structure, what I'm really talking about is actually to find a solution to the many electron Schrodinger equation, right? So, but there's a lot of complications come out of the Schrodinger, solving the Schrodinger equation, and there's also approximations. But even making approximations is not easy. So we talk about term symbol, which is a very nice way, also a very clever way of identifying out the energy levels of those many electron systems, right? So without solving the real Schrodinger equation, without knowing the exact formula of the wave function, we gain some knowledge about the energy levels. So in the previous lecture, we talked about why this is feasible. There's some fundamental quantum mechanical principles that support this. And to be simple, it is because those operators of interest, for example, the orbital momentum operator and the Hamiltonian operator, they commute. So in the language of quantum mechanics, that means they share the same pool of wave functions, no matter how complicated they are. So on one hand, we can identify how many eigenstates for their orbital momentum, and then we can correlate them with the pools of the wave functions and identify the energy levels. Today we're going to getting a little bit practical, and I'll start with a practical transition metal LH. Okay, and we're starting with the simplest one that we can ever imagine, which is D0, right? It should be very simple, but not really. Okay, and this is the simplest the system we can ever imagine when we have a D0, 3D0. Let's limit our discussion to just the 3D elements, okay? And that's the primary the area of interest we'll be working on for batteries. For the 3D elements, the simplest cation we can think about it should be titanium 4+. I mean, in terms of from the perspective of spectroscopy, it's because titanium 4+ is actually 3D0, right? So the initial state is a 3D0, and once the absorption is generated, the final state is actually a core hole. We have a hole in the 2p orbital, or we can write it as 2p5 now instead of a 2p6. Now we have 2p5. And this valence electron is promoted to the 3d orbital, right? So we have a 2-electron system where we have actually 2p5 and the 3d1. So that's the final state. Hopefully that we all agree on this. A side note of this is the absorption event is some sort of the first order decay process, right? So we shine the sample with X-ray, absorbs it, and this creates this completes the whole absorption process. So at least for the absorption spectroscopy. So we have an initial state that is a ground state. We have a full core hole, and then we have the final state, which is just a core hole and with a valence electron. But this is not the end of the practical situation, right? A lot of our decaying process can follow that. So for example, we can have the origin decay or the fluorescence decay. Those events are following this kind of, the first order decay process. So there are a lot of things to follow. So you can imagine there are more complications to consider. But for the absorption, it's, there's just a first order, and we can do some, I would say, relatively accurate calculations of this process. Okay, so for this state, we can in fact derive the term symbols for this many electron system, right? And the practical treatment is that instead of treating this as a 2p5, is actually treated as 2p1, because basically, when you're having a whole is equal to, having this kind of a 2p5 configuration. So we can directly derive the big S, the big L, and the big J if there's a spin orbital coupling, right? So we need to consider the big J. And the derivation of S is simple, right? Since we have the 2p electron, which has the 1/2 S, and we have the 3D is another 1/2, and they have different ways of coupling with each other, right? So the coupling, the interaction between these two spins is more like a vector coupling, right? So it's actually basically how the two vectors are added together. So this two would lead to two different possible results. So one is kind of constructive, so they would lead to the total S, the big S equals to 1, right? Or they could interact in a way that is destructive, so sort of canceling out, and we have the 0 for the big S, right? And by the way, hope that you still remember this term symbol that we have been discussing for the past 2, maybe 3 lectures, that this 2s plus 1 is called multiplicity, right? So this is called multiplicity. It's indicated by the total spin of the system, and we have this big L, which is the orbital momentum, right? If the S and L, they do coupling, they do have a couple, and we still have the J, right? And the J is the total angular momentum, including both the spin and the orbital part, right? So S, L, J. Now, okay, let me go back to deriving the term symbol for this 2 electron system. So now we learn the big S. We can also derive the big L, right? So for the big L, since the 2p, the L equals to 1. I hope you still remember the fundamental quantum mechanics, right? S means L equals to 0, and P means L equals to 1, and the D, L equals 2, and so on, right? So now we have the 2p electrons, so actually the L equals to 1, and we have 3D, and the L equals to 2, right? And they can couple also through a way that is a vector addition or subtraction. So basically, how these two vectors, they would interact with each other would lead to 3 results, right? You probably have the question that, why, since the vector, if the addition, there should be 3, if subtraction, there should be 1, then how come there's a 2 coming out? This is because they're not the pure vector the addition or subtraction principle, because in fact, when we consider about this 1 and L, we, instead of thinking them as a vector that has a length and direction, that is not enough. We need to consider them as a cone, right? It's a cone. Actually, it's cone in the space, and it's basically, it's not just 2 lines, directional lines adding or subtracting. It's actually 2 cones that is doing the interaction. So that adds more complexity. But at the moment, you can accept that, once we have the L equals 1 and L equals 2, we have the final big L that could be 1, 2, or 3. So this comes from combination of these two L's. But I hope you are convinced this is much easier than solving the Schrodinger equation for many electrons, right? This is simply just some simple algebra, and this is way easier than solving the Schrodinger equation, and that's the beauty and the strength of this. Okay, and after deriving the S and L, we now have in fact 6 term symbols for this seemingly simple 2 electron system, right? One hole and 1 cohole and 1 electron, right? So it may sound very simple, but you see, now even without considering the spin orbital coupling, we already have 6 states, meaning that once you promote a cohole to be electron to a 3D orbital, and it in fact has 6 possible energy states, right? Described by this 6 term symbols. I want to have a quick quiz here, so everybody heads up. Among these 6 states, which one has the lowest energy? So this is a test of your knowledge of previous lectures. Yeah, can you type it in the chat? And I'll drink some water. Okay, so Moimina said 3F. Any different thoughts? Everybody agrees or think he's wrong? I'll give 10 seconds. Okay, I guess silence means agreement. Yes, 3F is correct. So it's basically we're looking for the maximum multiplicity and the maximum orbital momentum, right? So Moimina is correct. Okay, and this is simply for the case without considering the spin orbital coupling, right? Let's get a little bit more complicated. And now we consider the case where, which is more practical when the spin and orbital actually do coupling. They're both the angular momentum, right? So they're they should interact with each other. And when we consider the spin orbital coupling, we still look at the same system. This is still 2p5 3d1, right? And we can do the same thing for the S and L. This is the same. We derive the S, right? We derive the L, right? Now we can realize that this S and L, they could interact also in a way that is similar to the vectors, not exact as vector, but similar. So now once we have this S, big S, and this L, they could interact, to produce either 1/2 and 3/2, right? So you can say this seems to be a simple subtraction of this one from this one, and this is simply the addition. It's close. It's close. If it helps you to understand why we have these 2 numbers for this kind of interaction. And similarly, once we have for the D electron, we also have this kind of coupling, right? We can have the same coupling for the 3D and for the D electron. So the D electron would be able to do different possible J's, right? So that's the 3/2 and 5/2. Okay, now we have actually the different J values, and I hope you still remember that this J in fact is actually also there expressed as 2J plus 1, right? So previous slide shows us actually we have a PDF, and now we add a third notation to this term symbol. So instead of just having their multiplicity PDF, we also have this kind of a total angular momentum and differentiating the different states. And now Yeah, I just want to have another quick test. So now what is the lowest energy state for this bunch of symbols? Any ideas? Okay, I just saved time and I saw the answer from Shar and she's correct. It's 3F2, right? Because we first look at the maximum multiplicity and the orbital angular momentum for these two parts, and we look at for the smallest number because this is a less than half filled orbital. I mean, in terms of the D, so actually we look at the small number. So this 3F2 is actually the lowest energy in this whole system. Okay, so we now realize that once we consider the spin orbital coupling, we actually have so many states possible for this simply 2-electron system, right? So it's just 2 electrons, but it has so many possible energy states. But the question is, are all those transitions possible? Or I could say, we are expecting to see so many peaks in the titanium 4+ transition metal LH? And the answer is no. And if you do a quick Google search of titanium 4+ LH, you will see that they definitely would not have so many peaks in the spectrum, right? So then, what are the possible states? And this goes to the transitions, the possible transitions, right? And we need to talk about the selection rule for the many electron systems. I think we have been talking about selection rule for a single electron picture for a long time, right? We talk about the S to P, which is dipole allowed. We talk about the P to D, which is also dipole allowed, right? We also always talk about the delta, the small l, that should be either plus or minus 1. So that's kind of the 1 electron picture we have been they're very familiar with in discussing the spectroscopies. But now we understand a more practical situation, which is the many electron system, and we know the many possible states in electron system. Then what's the selection rule for many electrons? The answer is actually we should look at the total spin, the total orbital angular momentum, and the total angular momentum. And this also, give us the confidence, or give us the feeling that the importance about term symbols, right? Term symbols, not just to give us the information about the possible energy states. It also tells us what are the possible transitions, because the term symbols is embedded with the symmetry information, right? So those numbers, the multiplicity of the orbital angular momentum, they are embedded with energy. So that's the quiz we just had. I'm asking which one has the lowest energy. You can tell them from their term symbol by looking at how big the number is, or what are the letters. They also bear symmetry information. For example, if there's a big S, it bears the S symmetry as a many electron system. So that's the beauty of the term symbol. And to summarize, the selection rule for the many electron system is, first of all, the total spin cannot change. And this is originated from the fact that we're exciting the whole system with photons, right? So that photon is not actually doing anything to the spin part of the whole system. The second part, we need to know that we're now looking at the big L. So if we do not consider the spin orbital coupling, then we should just look at the big L. Then it should be the big S to big P. It should be big P to big D, right? So that's the case for the case without considering the spin orbital coupling. But once we consider the spin orbital coupling, we should look at the J. We should look at the last place in this term symbol. And it is similar, but with some a slight difference is that we're still looking for a total change of J that is the plus or minus 1. But that's also possible if the J doesn't change. But this is only on the condition that J, the original J, is not 0. So it's getting a little bit more complicated. But for the moment, the key information we need to remember is the big J is following a similar principle as the big L. It should be a plus or minus 1J. Okay, so let's look at some applications. We'll still use the 3D0, titanium 4+, probably the most simple, the simplest transition metal LH spectrum we'll ever encounter, during the research. So if it's without spin optical coupling, so we see that the initial state is the ground state. We have no 3D electron. We have the full and 2p electrons, right? And once do the excitation, this is the final state we'll get, and it's 2p5 and 3D1. And by the way, in yesterday's discussion with Arthur and Dean, we talk about the core hole lifetime broadening, right? So you see now we have a core hole here, and this is core hole is contributing to the broadening of the peak. And that has the physical origin, which cannot be eliminated by any instrument update, right? So that's something intrinsic to the absorption. And this is also true for the hard X-ray, but in the hard X-ray, in that case, the final state is no longer a 2p5, it's 1s1, right? So we're knocking out the 1s electron out. So we're leaving behind a 1s core hole, and that is generating a very large core hole lifetime broadening, much larger than this one to the spectrum. So the hard X-ray absorption spectroscopy is intrinsically much more broadened than the LH. You can argue that, that as one of the advantages of using the LH, since we have a better resolved peaks that has the physical origin of that. Okay, so let's continue looking at the term symbol. So for the initial state, this is a very simple 1s0, and this applies to all the full shells, right? Once we have the full shell, you always have the 0 spin because all the electrons are paired up. So you have no spin, so your big S is 0, so 2s plus 1 is 1 here, right? Also, your total angular momentum, orbital angular momentum is also 0, since we have the full, the electrons, and the combination also leads to 0. 0, 0. No matter how you interact 0 with 0, you always get 0 as a result, right? So this is the initial stage, but this is the important, as we see it relates to how we understand the transitions, right? Okay. So for the final state, we have already derived this, right, in the previous slide. So we know there are 3 possible states for this kind of electron configuration. We have already done the quiz, and this one has the lowest energy, right? So now we look at the possible transition. We see that the spin doesn't change for any of them. The spin is always 1. So okay, in terms of spin, they are all possible. But what about the orbital angular momentum? For the orbital angular momentum, they can only be P, right? Because D and F violate the symmetry requirement for the dipole selection rule for many electron system. So no D, no F, only this one is possible. Even though we have 3 possible states, but only this one can be accessed by the absorption, right? Okay. In that regard, it seems that if we do not consider spin optical coupling, there should be only 1 peak. And I'll show you this is indeed the case in the software there a few minutes later, right? In the software, actually, we can mute the contribution of spin optical, and you'll see indeed this will produce only 1 peak in the titanium 4+ LH, which is pretty cool, I think. Okay, now with the spin optical coupling, now let's look at the case, right? We still have the 1s0 as initial state, but now, as I mentioned, since now we have spin optical coupling, we need to look at the J, right? And we have already identified the possible J's for the final state. Then we should be only looking at J equals to 1. Since I mentioned the J, following a similar rule to the big L, this should be only plus or minus 1. I mean the change of the J. So now we have actually this 3 possible states that can be accessed by the absorption event, right? So what that means is that if we consider the spin orbital coupling between in the electrons, actually instead of having 1 peak, we have 3 peaks, right? Okay, so now I think this is what I want to share with you about the principles or the fundamentals, right? And hope you have some impression about the term symbol, its importance, application to the transition metal edge. And now I'm moving to the other computer, which I'll show you how to use the software. So bear with me for a few seconds. Let's see. Okay. I'll stop sharing for the moment. And I'll switch to another one. Okay, just to jump off from here. Can you see me and hear me?
Yes.
Okay, great. Let me do the screen sharing again. Can you see my screen?
Yeah.
Great. Okay, the sound seems to be small. Okay. I don't know if you have already installed this software, and this is called CTM4XAS. So CTM stands for Charge Transfer Multiplet, and 4 means for the purpose of XAS, X-ray absorption. And this is a kind of old version, and this is what I used when I was a PhD. So that's 6-7 years ago or something. I think they probably have a newer version. A little bit more background information is this software was actually written by Frank de Groot from Lebanon, and the other author is actually his postdoc, Eddie Stavisky, who is the ISS beamline scientist at LISOS 2. So Eddie is actually the first author of this software. Okay, so let me cross out this, and I have opened it. You see, this is the interface, right? I'm sorry if my background looks like messy. Hope it doesn't interfere with your understanding. So this is the interface, and it has some, information. I think that is kind of obvious. We can start with titanium 4 calculation, right? So you can select. If you click this triple dots here, it displays the PR table. You can select the elements of interest. We'll start with titanium 4+. If you select titanium, it will ask what type of titanium you want to calculate. So let's start with titanium 4+, which is the simplest system, right? Also the 3D zero system. Okay, now titanium 4+ is selected. And also it describes initial state, which is obvious, right? We have the full 2p shell, subshell, and no electron in the 3D orbitals. And for the final state, we have an excitation from the core hole of 2p to the 3D, right? So, okay, so this is the final state. And it has some parameters, and some I'll explain in later lectures. I'll briefly mention them this time. So this is so-called a Slater integral reduction. So in case you didn't know, Slater is a very important person in their understanding of electronic structure. was a previous Harvard professor. So I don't know if I have ever mentioned the Slater determinant, which is a key element in deriving their multi-electron systems. So Slater is very important. And the Slater integral is basically some key integrals considering their interaction among different electrons. For example, this is considering the DD interaction, right? So there, I think I also mentioned this in previous lecture. Electron, they instead of, in addition to having just a Coulombic repulsion, right, which is easy to understand, they also have some, quantum mechanical interactions. For example, they have the exchange interaction, right? So, and also, and to be more precise, actually, they have the correlations. So sometimes you may hear the strongly correlated electron systems. The strongly correlated systems, meaning that actually the electrons, they have a very strong quantum mechanical signatures in their interactions. So this is considering D and D, this considering P and D, and this is also considering P and D, but this is mostly considering about the Coulombic part, and this is more like considering the exchange part. Okay, you don't really have to, we don't have to go to the depths about these parameters, because at this time we do not consider, those kind of electron interaction complications for the moment. Okay, in this panel, we have the crystal field parameters. So this is considering their specific geometry that cation is residing in, right? It could be an octahedral, right? It also could be a tetrahedral, right? And depending on what kind of site this cation is sitting in, it has a different symmetry. For example, if it is octahedral, it will have the OH symmetry. So this comes from, the molecular, the point groups that you have all sorts of symmetries. This is the OH symmetry. If you use a tetrahedral, you have this, let me see, it's D4H. I'm not very sure about this as a matter of fact. I thought it would be T4D. I wasn't expecting D4H, to be honest, but I guess this is symmetry for the tetrahedral. And if you have further distortion, right, actually it will lead to some more complicated symmetry configurations. But at this moment, let's just select OH, right, this octahedral, which is very likely the site for titanium 4+. And this is indicating the crystal field splitting energy, right? So if you're already familiar with crystal field or the ligand field, sometimes we have a strong ligand, right? That's kind of pulling their EG and 2G far apart, right? So examples include something like cyanide or the carbon monoxide. Those are very strong ligands, right? They actually pull their T2G and EG orbitals very far apart, right? We also have some very weak ligand. Right? A typical example includes, for example, the oxide system we deal with, the oxygen or the chlorine, the bromine. They are weak. So actually, the T2G and EG, they are not so far apart. So we have, considerations about, whether the electron want to pair or they want to go to a higher energy orbital, right? So I hope you have some knowledge of this, which will help you to understand the situation here. At this time, we do not have to consider any the crystal field splitting. So we simply put this number as 0, right? We just assume it's a spherical symmetric environment, not spherical. It's octahedral environment, but let's assume that the ligands are not doing anything to further splitting the orbitals. Okay, so they're all 3D orbitals, right? The 3D, they have the same energy. We do not talk about T2G or EG. Let's just bear with that for the moment. Okay, now comes the spin orbital coupling, and this is what we want to look at, right? Let's start with 0, meaning that we do not have any coupling for both the core electron and the valence electron. There's no consideration of spin orbital coupling, right? And let's calculate the spectrum and see what we have. And bear in mind, we do not consider anything, right? Every parameter is 0. We just simply mute all the contributions from their practical, their contributors. We simply consider this multi-electron system. And let's do the calculation. Run titanium 4, let's say nothing, and go. You do some calculation very quickly. Oops, I think it's interfering with my previous calculation. So let me see if I should get rid of that. Yeah, I just cross out it. Okay. Let's do it again. Nothing. Yes. Okay. So we do see only one peak in titanium 4 LH, right? That is because we're not considering anything, including the spin optical coupling. And this is the same as what we concluded previously when we showed the slides, right? And keep in mind, this is not saying there's only one state. It's only saying there's only one possible transition to all those multiple states. Okay, now let's consider the spin optical coupling, but consider first the core electrons. Let's put 1. Okay, we'll consider the full coupling. Let's run again. Titanium 4 core SO coupling. Okay, now you see we seem to have 2 peaks, right? After considering the spin of core coupling, we have 2 peaks. But in fact, there's a very small peak here. Because it's a very small intensity, we are not able to see obvious peaks. But if you trust me, actually there's 3 transitions, 1, 2, 3. And that's exactly what we concluded from previous, the principles, right? From the previous discussion on the 3D zero. Okay, we can get things more complicated, right? So now not just consider this the orbital spin coupling. We can also consider, let's say this is this ligand is exerting some force on electron state. So actually, instead of 0, let's put 2. 2 is some kind of a weak interaction. So this is in the unit of 2 eV, 2 electrons. So let's run again. Okay. Now we have titanium 4 and core SO, and also we have the 10DQ as 2 eV, right? So this is 2 eV. Let's see what it gives us. We're getting more complicated, right? So now we see that actually so I think it should be easy to tell. Let me show the ligand. So this magenta one has actually multiple peaks. We can roughly say, that corresponds to the T2G, and because the spin optical splitting, actually they are split into 2 parts. That's kind of some rough description, right? And we can get even more complicated. Let's say, so let's consider the electron repulsion, or let's say if we put this as 0.8 something. So this is basically some kind of a scaled parameter. So let's do it again. Consider the FDD. And this is also consider the FDD. 0.8. Let's do it again. Okay, so that's basically the same. So that means actually the DD electron repulsion is not really doing anything to the spectrum, which is not surprising since we only have 1 electron, right, involved in the 3D in the final state. There's only 1 electron. No considering of the electron repulsion is needed, right? But we can get more complicated when we do the nickel. Let's look at nickel. Since nickel is there something that we definitely encounter for the battery materials let's start with nickel 2+, which is very common. Okay, so now we're getting very complicated. In fact, the nickel 2+ in the initial state is already a multi-electron, many electron system, right? We have 8 3D electrons. And in the final state, we have 9 3D electrons, and also we have coho. And let's say what this one does give us. We also put everything back to 0 and see what it produces. Okay, so everything is 0, right? So now let's calculate nickel 2 and nothing added. Okay, so it also only gives us the 1 peak, and there, I believe this is also from the result of term symbol derivation. Let's get a little bit complicated by put their spin coupling, and I think we would expect that it will start to split peaks, right? Let's run again. 2 so spin coupling. Okay, indeed, it gave us 2 peaks. But now, because we have many electrons in the 3D, actually, we also need to seriously consider the spin of the coupling for the valence for the 3D electrons, right? Just not for the 2p. Let's put their also consider spin of the coupling for the valence electrons, and let's run again. And let's just add the valence SO. Do it again. So we see obviously some big change of the peak ratio, right? So this one is huge, and meaning that this one is almost gone, meaning that those numbers actually doesn't really make sense. So we need to adjust those numbers. And this software comes with a manual with a detailed description of what kind of numbers would be appropriate. So I believe this probably means we need to reduce this number to a much smaller value. This is too big for the valence spin optical coupling. So we need to scale it down a little bit. Okay, and let's just temporarily put it back to 0. So we do not have to worry about this. We can also now we can check the symmetry. Okay, let's say now we have 2 EVs crystal field splitting, and we run again. So now we have 10DQ. 10DQ has the spectroscopy origin, because actually it comes from the spectroscopy term that people is used to defining this kind of splitting as a 10DQ, because it's easy to calculate. Then you have the EG lowered by 6 DQ and the T2G increased by 4 DQ. DQ. So there, if you're curious about why it's 10 DQ, it just simply has the spectroscopy origin. Okay, so this is what we calculate. So you see now, once we have this consideration of crystal field splitting, which is in the practical case, we're shifting their energy positions, right? We're also changing the peak ratio, right? So now if we also further consider the electron repulsion, let's put a number here. This is some kind of empirical number. We consider the electron repulsion. Also, we consider the electron exchange energy. Let's say, let's put a post 7 here. So run again. So that is some more consideration. So now we have F, DD, and Q, no, GDD considered. Okay. Okay. I think this one, the first one and the last one, they all have blue. So I just delete the first one. They're not interfering. Okay. So now the blue, this green one is actually, I think it's probably getting close to the practical situation when you look at the nickel 2+ the spectrum, right? So you can play with all those parameters. And for some systems, you have a good chance of getting the spectrum that is very close to what you measured. And by changing those parameters, you do have some idea, what's the property of the system you're looking at, right? For example, you can change this 10dq, and you may realize that, okay, I have to increase it to a very big number. Let's say it's a 4 eV in order to, get the spectrum, the calculated one similar to my mirrored spectrum. So that's indicating, you do have a very large 10dq system you're dealing with. And as a result of that, your system probably is a low spin, right? Because if you pull the EG and 2DG very far apart, you end up with a low spin configuration. Okay, so yeah, so this is basically, there are some, kind of introductory tutorial for software, and hope you find it useful. And if you want to practice, I think you'll be fun, and you can discuss with me if you have questions. Okay. Yeah, I think that concludes my lecture today, and there is time for questions. Maybe I just leave it there in case you have questions specific to the software. Yeah, any questions?
Actually, if I can, it's more just a software question. I can't get it to go to the RIX mode or the XAS mode on the new software. Is there something I need to enable?
So you're ambitious. You're already exploring the RIX.
I was just like looking at it. It just is like grayed out on my. I can share. Oh, but it will stop you. Oh, sorry. But yeah, just on mine it's grayed out, and it's like a little bit different. I don't know if you. Maybe I should.
I haven't explored RIX,
Okay.
and to be frank, I don't know how reliable this software is in producing RIX, because as some sort of background, Wiley has been working on the RIX, right? So he's trying very hard to understand, the spectrum, and he spent more than 1 year working with a physicist from Stanford University, working on reproducing the RIX spectrum they measured. So that's some sort of the amount of work that required to reproduce RIX. So what I guess is that one possible thing is you see it only lists some specific configurations, right? And those may not include the RIX that we want to measure. The second thing is it probably would actually make some very bold simplification assumptions, which probably can distort the spectrum quite a lot. For the XAS, as I mentioned, it's a relatively simple process, right? So it's only in the first order decay we have the initial state, final state well defined, and you see we can almost do the hand, the calculation of the term symbol. So we already have some idea what they generally should be looking like. So this are relatively simple, right? So yeah, I would I would hesitate going to that part.
Okay. Thank you. Yeah, good point.
Okay. Any more questions?
I had a quick question.
Yeah.
When should we consider the charge transfer parameters? The CT.
Yeah, that's a very good question. Yeah, that involves more in-depth discussion on the transition method IIH. But I think we can have some, the beginning. So the charge transfer typically happens when your system is highly covalent, meaning that your 3D energy is very close to the 2p1. Right? We know they're close. So there's a lot of covalence involved in the 3D transition metal systems, but in some systems, they're so close. So it's basically, involving the charge transfer. And also the charge transfer includes both the metal to ligand charge transfer and the ligand to metal charge transfer, right? In some cases, actually the 3D, the resulting 3D energy is so low. In fact, it can be even lower than the 2p. it happens for some late transition metals. For example, nickel is one possible candidate, and also like copper. And those are very light 3D transition metals that the 3D energy can be really, really low, and the charge transfer can happen. So at the role of some, and then they're probably, you know, if you're dealing with some highly covalent system, you want to consider charge transfer. But my experience is, if your system is highly covalent, you probably want to be cautious using this software to do the calculation. You may not be able to really, you know, reproduce the spectrum you're marrying. And I have worked with cobalt and nickel systems, including cobalt 3, cobalt 4, nickel 3, nickel 4. My experience is that they work excellently for nickel 2+, okay for nickel 3, but far from satisfactory for nickel 4. Yeah, one of the possibility I doubt is it's because it's high covalent. In fact, I think you can gain some understanding from the fundamental philosophy of this software. You remember that we started with the free cations, right? So basically, we started with a model that is not considering the presence of any ligand, right? That's also how we started discussion. When we consider the 3D0 titanium 4, actually we didn't mention anything about ligand. We're simply considering some sort of a spherical cations that's, you know, that's just there. So you can consider you know, the inclusion of the ligands as some sort of a perturbation and to the original philosophy, right? Something added. So they were not really designed for a system that really involved their very strong interaction between the cation and anions or the ligands, right? So yeah, that's my thought on it. Any more questions?
I have one regarding the software installation. So
Yeah.
for this software, I think it mentioned that you also have to mention have to install 3 other packages.
Right.
Just wondering, do they need to be in specific pathway, or it can be anywhere?
I guess not. Maybe Momiler or Arthur, or Shar, I guess if you have already installed, you can give suggestions. This software was installed on my computer many years ago. As I mentioned, it was actually during my PhD. So that's why I want to switch the laptop instead of it getting myself bothered with you know, the installation process. I think that probably Arthur or Momiler or Shar can give you better advice on their installation. Yeah, but they're free.
Yeah, so I just installed. The only one that needs to be in the specific pathway is the COAN, which needs to be in the path that's specified by CTM4XAS, like the how to start it up. It just needs to be the C COAN, needs to just be where it's at. Everything else was I just put in wherever, and then it worked.
Yeah.
You do need the specific version of that MATLAB, the 9.0. You can't, like, I tried first doing the newest one, but then that didn't work. You needed the specific version, and then it all worked for me. Yeah.
What version of CTM4XAS you are using?
I
think
just
the latest one
download
was
the
6.
yeah. I have
Sorry.
6.1. I just downloaded
Yeah,
the latest
6.1.
one. Yeah.
Okay.
Any other questions or comments?
I have one regarding to the selection rule.
Yeah.
So for this spin orbital coupling system, we just need to consider the J we don't need to consider either S or L, the selection rule, right?
We need to consider J, but also we need to consider X, right?
Okay.
Because the S role is always there, no matter whether you want to do the coupling or no coupling, right? It's the S should not change. The big S should be the same as the final S, since actually, as I mentioned, we're exciting the system with a photon, which should not change the spin of the system, right? So the S to the S should not change. And when we consider the speed optical coupling, we just look at the J. We actually do not look at L in this case. We do not look at the big L. We just look at the J and see if J is following the selection rule, right?
Okay, so which means J is a like more dominant role, right?
Yeah, yeah. I think there. Yeah, I think you get the idea. Yeah, there. Yeah, when we have a spin of the coupling, J is actually very important, right? It's not only the basis of deciding which transition channel is possible, but also you can see that J is also determining the energy level, right? If we have the same S and P, and actually the final say is up to J.
Okay, yeah, thanks.
Yeah. And also, by the way, I think now you probably can understand, right? There, when we have the L2, L1 and L2, right? And they should roughly 1 equals to the 2P 1/2. I mean, the J is 1/2. The other corresponds to 2P 3/2, right? 3/2. And you can tell actually the 3/2 state is the lower energy, right?
Right.
So that's why actually the L3 is the lower energy than L2, right? Right. So I guess now everything makes sense, right?
Yeah.
Yeah.